Then you started combining the atoms of the elements to make compounds. And you made ionic compounds and you made covalent molecules. And you talked about what those ionic compounds and covalent molecules look like when you started getting into Lewis structures. So you looked at how the electrons were responsible for the reaction, or for the elements' reactivity to form compounds. After that, we took a brief moment and we started talking about balancing chemical reactions. In other words, we took those compounds and those elements and we started combining them to form new materials. And we said, if you're going to describe a reaction, you can't just tell me what the reactants are and what the products are. You got to give me more detail. So we included solids and aqueous when you started talking about your solubility rules for ionic compounds. And then we went on to say, hey, you can't talk about a reaction unless you talk about the energy involved. And we talked about enthalpy of a reaction. Now, after that, you spent some time getting to know the states of matter. At the very end of College Chemistry 1, you got to know what a gas looked like and the way it behaves and why it behaves the way it does. Then, when you came to College Chemistry 2, the first thing we talked about were the liquids, pure liquids. And we talked about how to determine their physical properties, such as boiling point, melting point, viscosity, vapor pressure, and stuff of that nature. So there's our gases, there's our pure liquids. We skipped the solids, the pure solids, and then we talked about solutions, which is our aqueous for the most part. So we went into more detail on those states of matter. Now what we're going to do is we're really going to begin the journey of the chemical reaction. Over the majority of the remaining semester, we're going to answer 3 key questions. In chapter 17, I think it is, it may be chapter 18, we actually answer the question, will the reaction occur as it is written? By looking at Gibbs free energy. Around chapter 14 through 16, our entire focus will be, 15 through 17, our entire focus is going to be how far does the reaction go? And chapter 14 answers at what speed does the reaction occur? So those are our 3 primary questions. What speed does the reaction occur? How far does the reaction go? And will the reaction occur in the first place? That's what we're going to answer the majority of the rest of the semester. Now, the how fast does the reaction occur is all based off of kinetics. And that is what we're going to start today. And what the lab on Thursday is related to as well. So let's just think about this. Let's say I start with concentration versus time. And we're going to look at it from the perspective of the reactants and the perspective of the products. Now, when you start a reaction, you got nothing but the reactants present. So you've got a very high concentration of your reactants, because that's all that's here. Now, as this reaction progresses, the concentration of the reactants will decrease. And eventually they're going to level off. They never get to zero. They may get close, but they're never going to get to zero. Now, why will the reactants never get to zero? Well, let's think about it. And I'm going to make you use your imagination. Remember, we're talking about speed here. Pretend all the tables and chairs are cleared out of this room. And on this side, I have you wearing a blue shirt, and on this side, I have you wearing a green shirt. And I make a blue shirt connect with a green shirt. And once you connect, you're done. You're out of there. But you got to stay scrambled in here, but you just don't move anymore. At first, it's going to be easy for those in the blue shirt to find the green shirt and vice versa. Because I got a big concentration of blue and a big concentration of green. But as time progresses, it's going to be harder and harder for a blue shirt to have to look around to see who's not connected already and find a green shirt that's not already connected. Well, the same thing goes for our reaction. You start out with lots of your reactants. But as time progresses, you're going to have less of these reactants. And before you want leveled off period. Because it's not likely for the one type of material to actually run in to the other type of material. I mean, if you're both moving around, the likelihood of the two finding each other becomes minimal. So that's why there's the leveling off. Now, for our products. Well, if we're talking about our products, we started out, there's absolutely no product. As this reaction progresses, you're going to make more product. Initially, you're going to make product quickly, but then again, you're going to level off because fewer and fewer molecules that haven't reacted are going to have more and more trouble finding each other.
So those who are just always going to be each other.
So this is leading in to rates of reaction. So if I want to describe what's going on, I can say that, let's say I have the reaction A plus B goes to form 2C. As A is reacting, so the change in my A concentration, again, delta meaning change in, we have the change in A concentration over the change in time. By the way, if you're not familiar with the notation from now on, when you see brackets surrounding something, those brackets represent concentration. Now, is A forming or is it going away? Going away. So we use a negative to represent the fact that you're losing A. Now, is equal to the change in concentration of B over the change in time. And again, because B is a reactant, we're losing it. Now, let's talk about speed. First of all, are we making or losing C? You're making C, so it's a positive value. So our change in concentration of C is going to increase versus our change in time. But you have to take into account the coefficient. And keep in mind, I have been making equal to one another. So to take and make that C equal, we would multiply that by 1/2. This is how you describe a rate of reaction. And folks, the nice thing is, now we can answer some questions. Let's say that the concentration of B goes from 0.6 molar to 0.1 molar over 10 seconds. What is the rate for the reaction of B? Well, B, first of all, folks, you can't have a negative speed. All these negative numbers are telling you is what? That they're being consumed. Negative does not mean anything but it's being consumed. You can't have a negative speed, can you? No, you hit 0, you're done. You can't go negative. You can't have a negative concentration, can you? No, you hit 0, you're done. All this positive, negative stuff, all it means is it being made or is it being consumed? It's just signed. So, to figure out the reaction associated with B, the rate of the reaction associated with B, it's delta B over delta T. So it's the final, so it will be B final minus B initial for their concentrations over the change in time. So in other words, we're looking at 0.1 minus, minus 0.6 over the change in time, which was 10 seconds. So this is in molarities per second. So we're looking at 0.5 divided by 10, which is 0.05. Molar per second. That is the speed at which we're losing this material. But again, we would report it as 0.05 molar per second as it. That's the speed at which the B is disappearing. Now. What rate? Of reaction for the formation of C. Folks, you don't have to do, you don't, obviously I didn't give you any information about C in specifically, but if we go back to our original equation, you will notice that what I did give you is a relationship between B and C. So that relationship was a negative delta B over delta T is equal to 1/2 delta C over delta T. So 0.05 molar per second is equal to 1/2 our delta C over delta T. So in other words, our delta C over delta T equals 0.1 per second, 0.1 molar per second. And again, this is definitely a positive. I mean, again, when we're talking about the rates of reactions, they can't be zero. All that negative at the B was showing us is that that is consumed. All the positive in front of the C is showing us is that that is made. It's just a way of declaring what's being consumed and what's being made. But you can't have a negative value. Questions? Okay. So the way we can describe the impact of each substance in a reaction is through a rate law. And rate laws have very specific forms. They will start with the rate, the speed. That's what rate means, folks, is the speed. That's just another term, is the speed. Is equal to the rate constant times a substance, could be anything, raised to a power, times another substance potentially raised to a power, and so on and so forth. Now, you can have a what I consider a monomolecular reaction, which depends on a single substance. You can have a dimolecular reaction, which means two molecules must collide with the correct orientation and speed. And you can have a what is called a termolecular reaction, which means you have three or more molecules that must collide with the correct speed. Now, basically, folks, the second one of these is the most common. Let's talk one. This first one means that the molecule has to break up itself. I mean, if we get under high heat or change the pressure, that is a possibility. But literally to have that monomolecular reaction, the molecule has to break bonds all on its own. Nothing helping it. It just does it. Molecules tend to be very stable. Reaction. Perfect. Now imagine evolution is now pressure. The right, you gotta have the high concentration, you gotta have the right speed, everything has to be there simultaneously. Three things colliding at the same time. That's a lot harder than two. It's not a matter of two going and collecting another one. When I say it's termolecular, I'm talking all three have to literally collide and hold on at the same time. Not very likely. So, dimolecular tends to be the most common because it means only two molecules have to connect. And that is possible. Now, the question is, how do we figure this thing out? How do we know what the rate law is? Well, we have some different methods. And we're going to talk about two of those methods, probably only one of them today. And the other one will be introduced briefly tomorrow in lab, but it won't get discussed until Tuesday. The first one is you can use what is called the method of initial reads. And the second one is called oh my brain just died on me. Integrated rate laws. I sometimes have trouble talking and writing at the same time. Doesn't connect. So, folks, you're going to use both of these for the lab you're doing tomorrow. So I'm going to talk about them each individually. Integrated rate laws, folks, that is easy. This one we're going to find out we can use graphs for. This other one, it requires you taking multiple samples. And it requires you knowing the concentration and of each of the substances and the rate associated with that material. I'm gonna do that one. Okay. So the method of initial rate. What we're going to do is we're going to collect a series of information. And let's say I have a reaction 2NO gas reacts with chlorine gas to form 2NOCl gas. And this reaction is being studied at a -10 degrees Celsius. I start out with some initial concentrations. And I start out with NO and my Cl2. We're not, by the way, we will use this notation where we put a 0 as a subscript. That means that not, as we call it, means initial. And then we're going to collect the initial rate. In molarity per, well, in this particular case, it's going to be per minute. Now, when I work with this reaction, I start out with 0.10 molar nitrogen monoxide and 0.10 molar of chlorine. And the initial rate for the reaction is 0.18 molar per second. Then I use a different combination. I use 0.1 molar nitrogen monoxide and 0.2 molar chlorine, and the rate is 0.36 molar per second. And then I change the concentrate or the concentrations again. I take 0.2 molar nitrogen monoxide and I react it with 0.20 molar chlorine, and the rate is 1.45 molar per second. Again, this is called the method of initial rates because I'm taking the initial concentrations and the initial speed. Now my general rate law will be that rate is going to equal K with the nitrogen monoxide raised to some power and the chlorine raised to some power. And what we are going to have to do is figure out what X and Y are. Now, the method is we are going to start, we're going to have to perform, in this case, 2 calculations. Calculation 1. We are going to hold the nitrogen monoxide constant and that is going to allow us to determine the exponent for the chlorine. Now you may ask why. Well, okay, so we're going to call this experiment 1, this one 2, this one 3. Again, for each of these experiments, we can write out this rate law. So we're going to take experiment 1, and if we were to write out the rate law for experiment 1, that would be rate 1 is equal to the rate constant, so it's a constant, times nitrogen monoxide 1 times chlorine number 1. We can write a second one, reaction rate law, rate 2, because I want to hold nitrogen monoxide constant, is equal to the rate constant, it's a constant, folks, times the nitrogen monoxide concentration number 2 times the chloride or chlorine concentration number 2. Now, if we take and divide on both sides, since we held the nitrogen monoxide constant, it means that, and oh, I forgot the X and Y, so let me get that in here. X, Y, Y. If we're holding the nitrogen monoxide constant, it means this part goes away. And it also means, because this is a rate constant, that that part goes away. So this becomes rate 1 over rate 2 is equal to the chlorine concentration for number 1 over the chlorine concentration for number 2 raised to the power of Y. Yes.
This is probably a silly question, but for the, those are the same. Why do you get rid of those and not get rid of the chlorine?
Because if you divide 2 by 2, they go away. So you're only keeping the things that undergo a change.
Oh.
So rate 1 I said was 0.18. Rate 2 was 0.36. That's going to be equal to chlorine 1, which is 0.1, divided by chlorine 2, which is 0.2, all raised to the power of Y. 0.18 divided by 0.36 is 0.5. And 0.1 divided by 0.2 is 0.5. And so this one is obvious. But let's say it's not obvious. How would you solve it? So the easiest way to solve it, if it's not obvious, folks. This one you could have figured out without doing any more math. But not all of them are going to be that simple. You can take the log of both sides. Or the natural log of both sides. It really doesn't matter. Log of 0.5 is going to equal y times the log of 0.5. Because when you take the log, the exponent comes out in front.
In your notes, you have, rate 2 over rate 1.
It doesn't matter. As long as you're dealing with the same one across and the same one on the bottom. So in this particular case, if I'd have done it rate 2 over rate 1, I would have gotten 2 is equal to 2 to the y. So it really does not matter.
Okay.
It's just as long as you keep one over the other.
Okay.
So log of 0.5 divided by log of 0.5 is 1. So y is equal to 1. Now we got to solve for the x. And we're going to do it the exact same way. But in this particular case, so now to solve for x, you're going to hold the chlorine constant. So I don't have to go back up. So if I want to hold chlorine constant, that means that I'm going to do rate of experiment 2 is equal to K times NO of experiment 2 raised to the X times Cl2 for experiment 2 raised to the 1 because we've solved it. And we're going to use rate 3 is equal to K times NO3 raised to the X times Cl2 3 raised to the 1. Again, folks, these chlorines now are going to go away because they are held constant. I said to hold them constant. And your rate constants go away. So this simplifies to rate 2 over rate 3 is equal to NO2 over NO3 raised to the power of X. Rate 2 was 0.36, rate 3 is 1.45. That's equal to rate or NO of experiment 2 is 0.1 divided by NO for experiment 3, which is 0.2 raised to the power of X. This comes out to be 0.248 is equal to 0.5 raised to the X. So if I take the log of both sides, the X will come out in front. So X comes out to be equal to Now we can write our rate law. The rate law for this reaction is that rate is equal to K times NO squared times Cl2 to the first power. A lot of times we'll leave the one off. Just like when you were writing formulas, you would leave the one off, we'll leave the one off. If it's raised to the first power. This would be an example of a term molecular reaction. Because two plus one equals three, meaning three molecules have to collide for this reaction to occur, the way that it is designed. You will be doing that in lab tomorrow.
Now that we know, but we have a
Not over this, just over the. I will be giving you questions related to the spec. The UV vis spec.
Oh, okay.
That's what your questions will be. It could be Beer's law related. It could be spec, UV vis spec related, but that's what it's going to be over, is something that you've already done. But I want to give you plenty of practice with this before I test you over. It wouldn't be nice to test you over it with only a little bit of practice. Okay, so what I'm going to do is I'm going to introduce the other one, but I'm not going to do a problem on the other one today. And then my goal is on Monday, I'll do more problems and I will have to edit the homework accordingly. So I'm going to take off the method of initial rates and I'm going to take off the integrated rate laws off of the homework that is due on Sunday. Because I want to at least introduce integrated rate laws briefly. And then I can actually go into more detail on Monday and do some more problems and add it next week. You had a question for me?
I did, in the homework, we had some homework, packet, we had to find K. The rate right there, how would we do that when the exponents are 3, because would it be meters cubed over the second?
Yes, so the rate constant is directly related to
Right,
the rate law.
so the.
So yes, it would be molarity cubed
It would be,
per time.
right, so then the final answer would end up being like, it would be meters squared or minutes or.
Right.
Okay.
Okay, so what I really want to do on the integrated rate law is just introduce some of the various pieces. Integrated rate laws that you'll be working with is either gonna be 0th order with and when we talk about integrated rate laws, we're talking about one substance within a reaction. We're talking about analyzing just one substance. Not, so we would be analyzing just the NO, for instance. We wouldn't be worried about what the Cl2 is doing. We'd just be focused on one of the substances. So 0th order. A 0th order reaction, the rate law is going to be equal to the concentration of a substance at any given time. T represents time. Is equal to a negative rate constant times that time plus the concentration, the original concentration, the initial concentration. This is going to have the rate constant unit. Of molar per second. Typically, or molar per time. Now, with respect to the lab tomorrow. You're going to evaluate the graph. And when you graph this, if concentration versus time gives you a straight line of y equals mx plus b, then you will know that it is first order with, zeroth order with respect to that substance. So when you graph concentration versus time, if you get the straight line, the y equals mx plus b, the best R squared comes at that point. Then you're gonna know that it is first order, zeroth order with respect to that substance. Now, first order. A first order is going to be the natural log of concentration at any given time is equal to a negative KT plus the natural log of the initial concentration. This one has a rate constant of seconds to the -1 or per second. Very hard to write that per second very nicely. And the way you will know that it is first order from a graphing perspective is when you graph natural log of the concentration against time. You get a straight line. I want to say it is a negative straight line. So that I'm doing it in my head here because I forgot my paper.
Do you get slopes?
I always heard.
The slopes are negative for the first two and then.
Oh,
positive.
okay, that would make sense. Sorry.
You want to hold on to it?
No, I'm good. I just drew, as you said, I drew this one wrong. Should be that way and that way
Okay.
because the slope is negative. Now, for the second order, folks, you will get 1 over the concentration at a given time is equal to a positive KT plus 1 over the initial concentration. This one will have the unit of per molar per second. So in other words, both of the units are in the denominator. And this one, when you graph it, you'd be graphing 1 over A, and that would give you the best line. And it's a positive slope. So what you're doing tomorrow in specific is you are collecting data. And I'm talking lots of data. I think it's like 40 data points for one run, and then you're collecting it for another. Now, tomorrow's experiment is actually setting it up fast because you mix 2 chemicals. You wait, you take a sample, you wait 30 seconds, and you stick it in the spec. You take it out, wait another 30 seconds, stick it in the spec. Take it out, wait another 30 seconds, stick it back in the spec. So you do that like 40 times for one sample. And then you mix another 2 solutions together and you repeat the process. Now, the first solution compared to the second solution is going to allow you to do the method of initial rates on one of the solutions. The data that you're collecting, the 40 points of data and 40 points of data that you're collecting, you're gonna graph. And you're gonna graph those 40 points using regular concentration versus time, natural log of concentration versus time, and whatever concentration versus time. And whichever gives you the best R squared tells you what order it is with respect to that substance. And that's what you're doing tomorrow in lab. So you just got a quick summary. So tomorrow, just expect to come in, take your quiz, and get started.
Are we, pushing up again, or is it just-
You will have to group up into 4 and 5 people again, because I still only have 5 specs. It's gonna be over last week. What does Bears Law tell us? Why the next must be the same thing. And right, and why do you use the blank you use? Basically, you use blank you use.